So take a look at what we've got on the board. Position is just the quantity value for our linear measurements, right? Well, for rotational motion, the quantity value is the angle. Displacement is just the change in position, right? Displacement for angular motion or rotational motion, and we're going to use those two terms pretty interchangeably, angular and rotational, is just the change in the angle, delta theta. And theta is the standard variable for measuring an angle. Okay, if you want everybody to understand what you're talking about, you use theta, unless you've got a lot of angles, and then, well, you're in trouble. Theta 1, theta 2, theta 3. Yeah, no, beta. We'll tend to use beta fairly often, though beta gets used for other stuff. Angular velocity. And look, it's a W. It's kind of curvy.
Lowercase omega.
Yeah, that's a lowercase omega. It's not a W, it's a curvy omega. It's a curvy W, so it's an omega. Okay, and it's just going to be, now by the way, what are the units going to be for that angular variable theta?
Radians.
Radians or degrees? Guess which one?
Radians.
Radians. Yeah, I know. Everybody's like, but I hate radians. No, radians are your friend.
Radians are so much better than degrees.
Oh, yes, degrees suck. Who thought of this? We're going to take a circle, we're going to break it up into 360 pieces. You idiot!
And then you have minutes, seconds, and all that.
I know, but you'll see why shortly, okay? And in fairness to Patrick, when I was sitting in general where he was sitting, I was like, radians suck, man. Let's just use degrees. But then I got to engineering school and realized what radians actually were. And I went, oh, no wonder. Okay, radians are cool, degrees suck. I'm sorry, we're going to talk about radians a little bit more. Because that whole dividing the circle up into 360 pieces really doesn't work very well. All right, so what are going to be the units for angular velocity?
Radians per second.
Radians per second.
There we go. Radians per second are going to generally be our units for angular velocity. How about angular acceleration?
Radians.
There we go. Radians per second, or radians per second squared. It's not that much different than the linear stuff that we've done. And because I don't do this very often, and you won't either, okay, note, this is not a required topic for the IB program. This is what we call an optional topic, okay? However, how many people are taking the AP test? Yeah, this will be on the AP test. Single team. Yes.
You can still sign up for that, right?
Yes. And in fact, that reminds me, if you did not sign up for the NIMSY review, which is coming up, and you would like the district to pay for your test, you have to go to the NIMSY review. Me personally, I would do away with all that. I go to the review, don't go to the review. I don't care. You get your test paid for if you get a 3.
Yeah, I like the whole if you study, you get your test paid for. That way it gives you a bit of safety.
I'm
net.
not buying that you necessarily study, but okay. If you haven't signed up yet, though, here's the point. And you want to take the AP exam, you want the district to pay for it, and you're going to sign up for it, you can still go to the NIMSY review. You paying attention, Brandon?
Yes.
Show up a little early
Okay.
so you can get everything filled out. Okay, I got an email from the science teacher in the district that runs the reviews, and she was like, yeah, they can still sign up if they show up early and get signed in. Okay, so you can still do that if you want to.
When is it?
Okay?
It's sometime this month. The last
It's like
Saturday.
January 27th, the last Saturday of this month. Okay? Yeah. Solo ensemble. Sorry. Qua.
So if we take physics 2,
Okay?
all right. So do we get to choose our option? Well, we do.
Actually, in physics 2, what I generally teach for an option is relativity. So let me couch that in 2 disclaimers here. The first one is that I'm not real great at teaching relativity, but the relativity option turns out to be really easy. Right? Everybody the first year I taught the newest relativity option, which has some stuff in it. I was like, Minkowski diagrams, you're kidding. These are so terrible to teach. Okay, yeah, whatever. But, yeah, actually, you remember when I said at the beginning of the year, time is always absolute, so it goes on the x-axis? Well, it will until you get to relativity. Then it gets to switch acts. Yeah. But at any rate, what I'm saying is this. Students went to take the test the first time, and they came back, they're like, yes, space-time diagrams are so awesome, that was so easy. And I'm like, really? Because my response to that is either, this is great, or this is going to be a disaster, because they thought it was really easy and it wasn't. But I got the test, and I looked at it, and I was like, oh, you're right, this is really easy. And they keep putting them on there, and they're really easy to work. And the relativity questions they give you, while there's a lot of depth available, they don't use all of it generally on the test. If they did, they'd kill everybody and they just curve it anyway, so yeah. And relativity brings up some very important, interesting points that it would be good for you to study. So I teach the relativity option. If you did some more studying, you could do the engineering option, because that's what we're studying here. Okay? I don't do that because most of the people that are taking physics 2 are taking because they're like, it's not so much that I want to get the credit for it from an engineering school as I want to learn about the cool stuff that I might never get a chance to learn about if I don't do it now. So we do relativity, and if time permits, we also study astrophysics, because neutron stars and black holes are cool.
Why don't you do that first?
Because astrophysics makes use of relativity. So if you do the relativity first, then the astrophysics makes more sense. Because relativity will require us to determine the requirements for a black hole, and then we use that in astrophysics as well. We've already done it, that makes it easier. Okay? All right, everybody good with this stuff?
Yeah.
Because we have other things to do. So, here's the next thing. Let's talk about this just a moment. Now, by the way, I don't know if Miss O'Keefe knows this. You can ask her. But I do know that we had a math teacher here for a long time, Mr. Taylor, who actually wrote his master's thesis in mathematics on the value of E. And he didn't know what the basis was for degrees. Why we decided, hey, we'll just divide a circle up into 360 parts. And I've never really looked it up, so I don't know either. But you should know what the basis is for radian. So let's talk about that for a moment and why it makes life so easy on these problems. So if we have a circle, like that, which while it's not a circle, it's close enough. And there's the middle of our circle. Yeah, I should quit teaching physics and become an artist. No, that's just starvation.
Isn't your dog
Yeah, that's
an
like,
artist?
what do you call an unemployed bass player?
A bass player.
Homeless.
Oh.
Wait, Mr. Blind, isn't your daughter an artist?
Yeah, about
Art
that.
majors is still useful.
By the way, the answer is the same thing to what you call a bass player that just broke up with his girlfriend. Poor bass players. Okay, so here's the deal.
Homeless.
We've got our circle, we've got our radius. Please put this in your notes. I know, we don't all understand this completely, right? Put this in your notes. Because it's going to be about a third of my students that are going to go, oh, that's what radians are. Okay. So here's how this game works. If we take the radius out of the circle and bend it a little so that it fits on the circumference. Ready, okay? We're going to take this radius out of here, bend it, put it on the circumference so that this arc length is one radius. Everybody okay? Then, that angle theta, that angle theta is 1 radian by definition. That is how we define a radian. we were to keep putting radii on the circumference of the circle, how many of them could we fit? There we go, 6.28. 2 pi. Make sense? Note, side note, sort of a TOK note type thing. If I taught geometry and we wanted to know what radians were, everybody would bring in a canned good. That would go to the local food pantry after we were done. And you'd measure the radius. And you'd put it down on your table. And you'd mark a little spot on the rim of the can and on the table. And you'd roll it out till it got back around once. And you'd measure the circumference. And you'd take that for all the cans that got brought in with all the different diameters. And you'd graph the diameter versus the circumference. And the slope of the line would be pi.
It's so extra. Not needed.
Right?
Yeah.
Anybody good? Now, here's the other thing about this. Note that if we got something like this,
It'd be like, oh, you said in eighth grade, important in eighth grade.
a wheel with a point on it, okay? And we rotate this point through 90 degrees, also known as
Pi halves.
pi over 2. What distance did it travel along the circumference?
1.47 radians.
There we go. Multiply, okay, the angle, pi over 2, by the radius, and you have the distance. Guess what? This game works for all angular variables. If we go back to the previous screen,
I only read that because that's what we do.
right there, multiply the angular displacement by the radius, and you get the linear distance, careful, not displacement, but the distance traveled along the circumference.
S equals R theta.
Multiply the angular velocity by the radius, and you get the linear, careful, not velocity, speed. Because the direction keeps changing, right? Multiply the angular acceleration by the radius, and you get the magnitude of the acceleration or rate of change of the speed for a point on the circle as it goes around. That is so much nicer than degrees. Degrees just make me want to shoot myself in the face.
And also you have to deal with bigger numbers. So it's
Yeah, exactly. This is easy. Any questions about this? All right, next thing. Don't write it down yet. Don't write this down. Okay, we've taken care of that. Okay, do not write this down now. I'm going to put it up on Google Classroom. I'll put the whole PowerPoint up. This table needs to be filled in for homework for Tuesday. Not Thursday, because what are we doing on Thursday? Right, refraining from crying. So convert all of those linear equations into angular equations, and then write out what the angular equation says in English. So I'm going to do the first one, just so that I'm sure everybody should understand. The angular equation would be that the average angular velocity equals delta theta over delta t. So to write that out in English would sound a lot the same, but not quite, because I'm not going to use a theta or a t here. I need full words. Okay? The average angular velocity equals the angular displacement divided by the time interval. Everybody okay? Same thing for all of those. I thought about going through and changing those to variables that are on your data and formula sheet, except there's nothing quite the same as those for the angular ones. Okay, so do this, write it out in English. It's homework for Tuesday, because we won't be here on Monday. 3-day weekend.
Wait, is that this weekend?
I love working for kids.
Yeah.
Hey, trying to go to Austin.
All right, everybody good?
The weekend.
Awesome.
No, I've been
Hey,
doing
look, it's the end of the lecture. Great, which means we have lab. Yay!
Well,
Okay.
actually, that'll help my test grade, so.
You better hope I heard it, because lab data is due at the end of the class period. You don't have to have a cover sheet. Listen carefully.
Yeah.
This lab is called Torque and Center of Gravity on the website. Torque and Center of Gravity, preliminary measurements. You're going to need to measure and record the mass of the meter stick, and record the mass of a binder clip and a hanging mass together. Everybody has a 200 gram hanging mass. Got that? Everybody gets a 200 gram hanging mass. Okay? Everybody gets ring stand and iron ring. Everybody gets binder clip. Good? Any questions about this? Okay? And then what you need to do is you need to, where did Mr. Rodriguez? Just fine. What you need to do is, first round for part A, is you need to balance the meter stick on the neck of the iron ring. No, not the circular part up here, the nice straight part up here. And note, clearly it can be done because I have a photograph of it. And we have this one up here, right? And when you do that, you need to record where the meter stick was balanced, okay, on the ring stand. Everybody good? And you're to use the 1/2 centimeter precision side of the meter stick, as it says in the handout, right? Then you need to add the binder clip. I didn't ask you to do that. Stupid iPad. So that it balances like this. And you're going to have to record where the meter stick is at on the iron ring and where the mass of the binder clip are at. Only one minor issue here. The binder clip covers up the numbers you're using to take the measurement.
Perfect.
You're welcome.
Wait, that's it?
Okay? So note that you're using the 1/2 centimeter precision side of the meter stick for all of these measurements. And you're going to have to tell me about how you decided on your uncertainties.
Yes.
And last but not least, you're going to have to tell me about how you decided on the position and uncertainty for the mass and the binder clip. Note, if you have any uncertainties larger than 1 centimeter, you're going to lose marks. So you better be able to explain, and you better have values less than 1 centimeter. Got it? Or equal to. Brandon, question?
No, I'm just
No?
thinking.
Think by hitting yourself in the head. All right, any questions?
Fully.
Yeah.
Self-use.
1, 2, 3, go. Data by the end of class.
Hey David, can you grab this?